Hello, everyone. I welcome you to my master's thesis presentation. The topic of, or the title of my master's thesis is Unlocking the Potential of Lignin as a Versatile and Green Additive for Future Materials. My name is A.Kaburi, and my examiners are Professor Ramal Layak and Homan Nate. So, my agenda for this particular uh, thesis presentation is number one, to look at the background to the problem, and that is why lignin matters in the shift from combustion to high-value sustainable materials like lignin. And the aims, we'll also look at the aims of my thesis as well as the questions or the questions that guided me to do my review to set out to explain how coating and film applications work with the use of lignin. I also talk about some key core findings that I found during my literature review in terms of the structural property links, the lignin types, modification pathways, and coating functions for lignins, and also identify some research gaps that are currently existing because of the immature or the innovative or the newness of how lignin and its futures work and how future studies should be prioritized. So why the topic matter is that we all know that lignin is one of the second most abundant renewable biopolymer after cellulose, and it serves as one of the significant natural resources. That is natural resource which is aromatic in terms of this structure, and also serves as a sustainability to replace the current fossil materials that we have been using. Although it has produced at more than 100 million tons annually, most of the industrial lignins are still utilized for burning for low value heat and power production, according to previous research by Fezeli et al. 2003 and Rakogas et al. 2020. Its dysfunctioning nature provides it with a structural backbone and phenolic groups, and making it one of the key areas to invest in for UV light absorption, antioxidant activity reaction of free radicals, and many other uses, including antimicrobial and flame retardant activities. All these are key functions that lignin is able to provide us. And this combination forms the basics and the compelling argument of film's activity, and as well as bio-based coating with the use of lignin. So the objectives that guided my review is that I wanted to assess how lignin can function as a multifunctional green additive for bio-based UV protective coatings in terms of thermoplastics, and for linking lignin structures, how the modification strategy will work, the loading level, and the film coating performance when we use lignin. And the scope of my review is that it focuses on the polymeric coating and filmings, especially waterborne and solvent-borne, and waterborne, solvent-borne, and bio-based systems, while I excluded fuels, bulk composite adhesives, as well as energy storage carbons. I used three research questions guided my review. One is, how do lignin types, in terms of where they are being their source or extraction, their structures, that is the SGS ratio, and the modification strategies systematically influence the optical, that is talking about the UV transmission, the yellowness, and the mechanical as well as the barrier properties of the coating when it is being used in this form formation. And the second research question that guided my review is, what essential trade-offs exist in lignin loading optimization, and which modifications can reduce these aggregations and its embrittleness, as well as the compatibility problems when it comes to waterborne or industrial systems. And last but not the least research question that guided my review is that, to what extent have lignin-based coatings, that is, it's being used for UV or antioxidant or antimicrobial or flame retardant, have been achieved? To what extent has it been achieved? And what are the design rules that can be derived from these existing case studies? So to move ahead, we would like to look at the structure, the chemistry of lignin, and I'll have a simplified structure in my next slide. But why the structure matters is that lignin acts a more structural family, more than just one common biopolymer for the relative abundance of the SGH, that is the different kinds, strands or units of lignin that we have, according to previous research. And when it comes to the coating implications, unit composition as well as the linkage distribution govern this reactivity, as well as the polarity and the molecular weight, and the thermal behavior, as well as the compatibility, and thus also affect the film performance and the surface performance of the lignin when it is being used. So it is so important that we know how the coating implications works in terms of the linkages, and that is the simplified or the chemical structure behind lignin for us to be able to determine these properties and how to use it for our protective coatings and filmings. So this is the simplified structure, and I mentioned earlier on about the three kinds of structures that or units that we can have in lignin. And over here, we can see the H structure. We see how it's been done. It's structured in terms of the double bonds and the single bonds. And when we see here also, that is the gene lignin unit. We see how it's also being structured. We see that over here we have an oxygen bond, which is bonded to this particular structure. And in the last but not the least, which is the X lignin unit, we see that we have oxygen bonds at the opposite sides of the main structure. So this is basically how the simplified structure of lignin look like. Now, the lignin types. Now, we can have lignin types, and this lignin type, each of them have different properties in terms of how, and these properties in turn influence how their coating relevance work. So when we look at this particular table over here, we see that we have the craft. The craft, its extraction method is usually the alkaline craft pulping. And we see that one of the main properties is that it has sulfur containing, it's also condensed, dark, and it has a phenolic rich structure. And when we look at its coating relevance or how it functions, we see that it has strong UV and antioxidant potential, but it is often in the form of a color, and the compatibility also has a little bit of challenges. When we look at the organosolv, lignin type, we see that it's organic, it has an organic solvent pulping method. That is how it is being extracted. And one of the main properties also is that it also has sulfur-free, it is purer and lighter in color, but it has it's lower in terms of its ash that it produces. And the relevance of this is that it is better suited to transparent or light colored coatings. So when we are looking for types of lignin that is suitable for light colored coatings, then we have to go in for the organosolv. And by doing so, extracting and using the organic solvent pulping method to be able to maximize this particular function. Now, the second type of lignin, that is the lignosulfonate or the lignosulfonate. That one, the extraction method is usually the sulfide pulping. And one of the main properties that it has sulfonate, of course, that's why it is called lignosulfonate. It has a water-soluble nature. It is multifunctional. And one of the main relevance of this particular type of lignin is that it is useful in waterborne systems because it's a good binder, and it's also a dispersant. And so that is also one of the main features and its function for the lignosulfonate. And the type of, the last but not the least, what we want to talk about here is the soda, which is the alkali pulping method without the addition of sulfur. So that is the main property, that it is sulfur-free. That is why it's soda, so it's sulfur-free. And it's also structurally variable. And one of the main relevance or the function is that it is promising for sulfur-sensitive situations or formulations. So if we are in a particular situation where we want to have a sulfur-free or we have a sulfur-sensitive situation and want to use a lignin material for coating, then the best one we have to go for is the soda type of lignin. And each of these also, we can talk about them in terms of the sources. So the source usually determines where the kind of or the type of lignin strand that we can get. And so for the softwood tendency, it usually produce a gene range lignin. And this usually show higher thermal robustness and more condensed behavior. And the hardwood, so the softwood tends to produce G strands, and while the hardwood can produce both G and S. And then for the practical lesson of this nature, we say lignin source selection is not in detail, and it directly shapes the optical and rhetorical as well as the mechanical outcomes of the functions of the lignin. Now, to move ahead, we'd like to look at the modification pathways. How can researchers fine-tune this particular load lignin to coating grades that will bring about the better function of it? Now, the chemical modification, we can talk about acidification, we can talk about epoxidation, we can talk about grafting to reduce polarity. We can also improve the miscibility, and sometimes we can also lower the color while preserving the UV active motifs. And these are all bound or being is researched by previous research. We can also look at one of the modification pathways talking about the nanostructuring. And in this particular modification pathway, we'll talk about lignin nanoparticles, which are often between 50 to 300 nanometers range. We can improve their dispersion, and this can enhance the antioxidant and the antimicrobial performance at lower loadings. And the last but not the least modification pathway that I looked at in this thesis is how the greener pathways, which is the mild and enzymatic route, can use the green pathways as an emerging way. But they must remain largely proof of concept, and they are rarely being reported in terms of full coating performance or industrial scalability. What can lignin do in terms of their performance in coatings and films? I've already mentioned a lot of them, and these are also some few that I want to summarize in terms of the main functions and the benefits of lignin. Number one is that it can help UV protection through aromatic chromophores and conjugated structures. We have already looked at the structure, and all these structures, depending on the type of lignin strand that we are looking at, can we bring about UV protection through aromatic chromophores. Number two is that it also has antioxidant activity through phenolic hydroxyl groups and can help in radical scavenging. And the third one is that it has antimicrobial activities that can prevent microbial activities on the surface, especially when it is in active packaging or it is used in nanoparticle surfaces. And the last but not the least is that it has flame retardant and barrier benefits through char formation that can help to prevent flames or to bring about torches in terms of diffusion pathways. Now, the typical trade-offs when I looked at the literature is that there is higher lignin loading improves UV shielding, but it often increases opacity and yellowness. So if you have a high lignin content in a particular surface or packaging material, it is good. It can improve UV shielding, but it can also bring opacity in terms of the yellowness of the appearance of the main product or the surface packaging. And the second thing is that the aggregation and pore dispersion can embrittle the film and reduce transparency. It can also have barriers in terms of, and the microbial activity grains are highly dependent on compatible and morphology. So it means that the compatibility and the morphology must be done well. Otherwise, the barrier and the antimicrobial gains will not function really well. Also, it also has the multifunctionality is promising, but the co-optimization in the data sets remain very rare. So that is why we need to also be careful when we're looking at the lignin for future coating. Research gaps identified and why the field is still premature. Now, there are fragmented data sets. So because of the fragmented data sets, most studies examine only lignin types and in one matrix under either a unique protocol, which makes it cross-examination or meta-analysis very difficult. And secondly, is that the research gap that I identified is that there are missing standardized descriptors. That is critical data such as the SGH ratio, phenolic content, the chromophore density, the color metrics, as well as the sulfur content are often also incomplete according to Leo et al. 2024 research that was conducted. There is also a scale-up the mismatch. Many formulations rely on solvent-heavy laboratory methods that are not aligned with waterborne industrial coating lines. And the last but not the least research gap that was identified is that very few studies quantify the UV, the mechanics, the barrier performance, antimicrobial actions, and the fire behavior together in the same series. These are research gaps that are very, very common in the current system of research that is being carried out that need to be looked at in the future. Recommendations for future research. So one of the recommendations that I will recommend from this my review is that standardization of lignin descriptors should adapt to a set which includes the SGH, the molecular weight, the PDI, the phenolics, as well. That is the AAI ratio and the sulfur content. That is the color and the TG of the lignins that we are looking at. So any research that we'll do in the future should be focusing on the standardization of the lignin descriptors that will adapt the sets which include the SGA, the molecular weight, and so on and so forth. And then secondly is that we should use similar lignin types to cross-compare and identify testing conditions to distinguish the chemistry effect from the processing effect. And last but not the least is that future research should focus on big paint, waterborne, and multifunctional coatings in comparable for performance and sustainability. This was also identified by Ru et al. In 2023, according to their research. In conclusion, I'd like to say that lignin is a very promising renewable additive because of its aromatic structure, which supports UV blocking and antioxidant activity as well as antimicrobial activity because of its char formation. And its broader use is still limited by heterogeneity, dark color, poor miscibility, and lack of standardized performance metrics. The best path forward is to better characterize and better modify lignin design for specific end-use targets. Overall, this thesis supports lignin transition from a low combustion byproduct to a high volume multifunctional material. This is the end of my presentation. These are the references that guided this presentation as well as my thesis. Thank you very much for your attention, and I look forward to your questions.